Okay, so we studied the bias variance decomposition as a a tool for decomposing the out of sample error, the expected out of sample error, in terms of bias and a variance. Okay, and it's relatively straightforward to add noise into that decomposition, especially when the noise is measured by the variance of the measurement error. Okay, so let's just do that, and then let's interpret the result, and it gives us a nice way to sort of see how changing the hypothesis set or changing the learning algorithm or what have you will affect the out of sample error by trying to optimize the various terms in this decomposition. Okay, so the bias variance decomposition with stochastic noise. Okay, so that's what we're going to talk about. And I'll just remind you, the bias variance decomposition when there was no stochastic noise was that the expected value of E out was equal to two terms, which was, the bias plus the variance. Okay, and what was this term? This was, in some sense, G bar of X minus F of X squared. And this term was the variance of G of X, where, the variance and this expected value and this variance and this average function that you output are all with respect to the randomness coming from the data set generation process. Okay, so when you generate random data sets, there's some average. So this is E out of X. So there's some average value you will output, and there's some variance. Okay. And let's see what happens when now there's noise. So how did we get this? Okay, so now the E out of X was equal to G of X minus F of X. Okay. And this was in the noiseless case. In the noisy case, E out of X is going to equal G of X, okay, minus Y squared. Because now, we're looking at the output Y, and the output Y compared to the prediction G of X, and the output Y is equal to F of X plus your noise, epsilon. So this is equal to G of X minus F of X minus epsilon. So this is equal to G of X minus F of X squared plus twice epsilon G of X minus F of X plus minus plus epsilon squared. Okay. Now, we're interested in your expected out of sample error, so let's take the expected value on both sides. So this is E out of X. So the expected value on both sides gives me the expected value of this guy minus twice the expected value of this guy plus the expected value of this guy. Okay. Now, if your noise, your measurement error is zero mean, so it's equally likely basically to be positive or negative, so you can equally likely make mistakes, up or down. Okay. Then, and assuming that your measurement errors are independent of basically F and G and X, so the measurement error is this totally independent random measurement error, then this is the expected value of two terms that are independent, so you can separate the two terms out. This is the expected value of epsilon times the expected value of G of X minus F of X. The expected value of epsilon is now 0. Okay, so this term is 0. And so we end up with the term that we had before, averaged over data sets, which this term is exactly equal to the bias, okay, plus at X, plus the variance at X. Okay. And then the expected value of epsilon squared, if the expected value of epsilon is 0, this is just the variance of the noise, so plus sigma squared. Okay. So let me summarize. Let's summarize that your expected out of sample error, and you can view it either as a function of X, or you can take the expected value over X. Okay, so the expected out of sample error is equal to your bias plus sigma squared plus, make these pluses in black, plus okay, your variance at X. So let me write that in black. So your variance, just variance. Okay, because we've taken the average, let's say, with respect to x. Okay, and let's interpret this. This is a very interesting breakdown. And this is an equality. So your expected out-of-sample error is your bias plus your measurement variance error, measurement error variance, plus the variance in the final hypothesis, okay, that you output. You can think of this, the bias, remember it's G bar minus F. Remember when we discussed bias variance, this is what? This is, you know, the best you can do. It's how well you can do. Okay. So how well you can do basically quantifies the deterministic noise. Okay. It's sort of the difference between the best H star in our previous discussion and F. Okay. And H star is roughly speaking G bar of X. So this can be interpreted as the deterministic noise. Well, this guy is exactly the stochastic noise. By definition, it's the variance of the measurement error. So this quantifies the stochastic noise. And this variance is the interesting guy. What is this variance? This variance is in some sense the indirect impact of these two types of noise. Okay, what is it arising from? It's arising from the fact that every time you generate a data set, you might output a different final hypothesis G. And the more noise there is, the more easily it is to be led astray and output random, wild final hypotheses. So if there's no noise, you'll pretty much always be outputting the best you can output, which is close to F. Okay. But when there's noise, okay, the variance is the indirect impact of the noise. And that's both kinds of noise. Okay. And that indirect impact can depend on your hypothesis set H and the number of data points, very importantly. The more complex your hypothesis set, the larger this indirect impact. But also, it's possible that the bias gets smaller, but you still have this guy here who's going to lead you wildly astray. And it's always the case that there's noise in data, measurement error. And this guy is going to prevent you in a significant way from going to larger and larger, more complex hypotheses. That's due to this variance indirect impact. Okay? But the sure way to lower the variance is to increase n. When you increase n, increase the number of data points, the impact of the indirect impact of the various noises gradually drops away, and then your out of sample error will basically be basically be the sum of, you know, the deficiency of the hypothesis set measured by the bias and the measurement error. And those you cannot overcome no matter how many data points you get. Okay? This is a very nice breakdown of your expected out of sample error. And when you're designing hypothesis sets and learning algorithms and so on and so forth, you can always look at this decomposition, even though you cannot measure any of these, and ask, am I trying to lower this guy, the bias, or am I trying to lower the variance? You cannot lower the measurement error. That's just measurement error. So this is there always. And through this, you will feel the impact in the variance. Okay, always. Okay. So this guy will feel this impact. You can try to lower this, but therefore you might increase the impact of this guy by a larger, more complex hypothesis. So a lot of interesting challenges for the machine learning expert and a lot of interesting choices that the machine learning expert has to make. And this decomposition can help a lot in making those decisions. Okay. So let's erase or